In this lecture, we will be discussing about acids and bases. So let's begin with some common acids and common bases that we usually use in our household. For instance, acetic acid, which is one of the flavoring agents used in our food. It's essentially just vinegar. The other acid example is citric acid. Ascorbic acid, which is essentially just vitamin C, which we consume, right? The some common bases that are used, most of the bases that are used in our household are used for cleaning purposes. For instance, sodium hydroxide, or cleaner like ammonia, sodium carbonate, or sodium phosphate. So these are some of the very common acids and bases that we usually use. So now let's look at what is the actual definition of an acid. So the first definition of an acid and base that was given out was in terms of how a substance behaves in presence of water. So acid was regarded as any substance with a proton. So essentially, it should consist of this hydrogen in its formula, and it would dissociate to release this hydrogen, and that hydrogen would react with water to produce H3O plus. And a base, on the other hand, was regarded as a substance with an OH in its formula, and it dissociates to yield an OH minus ion. So whenever an acid reacts with a base, it would undergo a step of neutralization such that H plus from the acid would react with OH minus from the base to produce water. Now this is called the Arrhenius acid-base definition, which applies to some acids and bases, but it does not apply to all the acids and bases. So the definition was revised, and there's another definition that was given by Bronsted and Lowry. According to Bronsted and Lowry concept, an acid is a substance that donates a proton, and a base is a substance that accepts the proton. Proton essentially is just H plus ion, which can also be referred to as, or very commonly referred to as, a proton, because H plus essentially has no electron, and the elementary particle that it has is a proton. So that's why this is referred to as a proton as well. So a proton donor is an acid, and a proton acceptor is a base. So for instance, let's look at this particular reaction right here. It states that water reacts with HCl to produce H3O plus and Cl minus. I just wrote this out, wrote out the equation right here. So essentially what's happening in this case is we see HCl, and in the product we see it has been converted into Cl minus. So what happened here is this HCl essentially just lost one of the protons and got converted into Cl minus. On the other hand, this water has been converted into H3O plus. So what happened here is this proton that was donated by HCl was accepted by water, and it accepted this proton and made H3O plus. This is another form of proton. So usually protons, when we say H plus, they don't exist in this form, and they react with water to form H3O plus. So that is also another very common feature that you're going to see in this case of acids, how acids behave in water. So in this case, since this particular compound right here, HCl, is the donor of proton, it's regarded as an acid, whereas H2O, which is water here, has accepted the proton, it's regarded as the base. So that's essentially what's the definition of an acid and base by Bronsted-Lowry concept. It again states that base reacts with acid, and this step is called neutralization. So that hasn't changed. Only thing that has changed here is that we don't have to regard that every acid has to have an H to become an acid. Okay. So let's see some other examples right here. So in this reaction at the bottom, HClO3 aqueous is reacting with water to produce H3O plus ClO3 minus. So essentially what's happening is HClO3 is changing into ClO3 minus. So what this is losing here is essentially H plus, and this H plus has been accepted by H2O to form H3O plus. So again here HClO3 has donated the proton, that makes it an acid, and water here has accepted that proton, so that makes this a base. In the next example, you can see here NH3, which is essentially ammonia, reacts with water to produce NH4 plus OH minus. So what's happening here is that NH3 and water, NH3 has changed to NH4 plus, meaning this has accepted a proton in here. So if it has accepted a proton, that makes this a base. And water, on the other hand, has changed into OH minus. So water here donated a proton, and that makes water an acid in this particular reaction. And you can see that ammonia here is acting as a base. According to the previous definition by Arrhenius, any base is a compound that essentially has OH in its formula. And you can see right here, NH3 has no OH. Instead, it has actually an H in its formula. But this is a base. So that's one of the examples that shows that why Bronsted-Lowry concept or definition was actually needed to redefine acids and bases. Okay, but the concept is still the same. So you can see here ammonia is reacting with water and eventually it's producing OH minus. So that idea is still correct. It's producing OH minus, but it does not have the OH minus in its formula. Okay, so one is a proton donor, another is a proton acceptor. And you'll see later on that there is another definition for an acid and a base, and we'll talk about that later on. But this definition is also holds true. Okay, right. So another concept that you're going to very commonly see in case of acids and bases are the conjugate acid-base pairs. So what does that mean? For instance, let's take a look at this particular reaction where H2S is reacting with ammonia to produce HS minus and NH4 plus. So let's look at a forward reaction right here. Now you guys remember from the chapter of equilibria that most of the reactions are actually in the state of equilibrium, meaning there is a forward reaction and there's also a reverse reaction. So let's just look at the forward reaction to begin with and define what is an acid and what's a base in this case. So here what's happening, H2S is actually losing a proton and changing into HS minus, right? So that makes this H2S an acid according to Bronsted-Lowry concept. And what's happening to ammonia, ammonia here is changing into NH4 plus, so ammonia has actually accepted a proton. That makes ammonia a base. So whenever an acid changes into something in the right, this essentially is called as an acid-base, conjugate acid-base pair. Okay, what do I mean by that? So in this case, first thing, let's just write this down. So H2S and HS minus. This is one of our conjugate acid-base pair. The second acid-base pair in this reaction is essentially NH4 plus and NH3, which is also an acid-base pair. Now let's see, what do I mean by the other reaction? So hopefully this part is making sense to everyone. H2S is an acid and ammonia is a base. So let's look at what is the other. So now let's look at the reverse reaction here. So what's happening in the reverse, if you believe these are our reactants now, HS minus and NH4 plus. So if you're going in the reverse direction, what's happening here? NH4 plus is actually losing a proton and changing to NH3. Right? So here NH4 plus in the reverse is donating a proton, which makes this an acid in the reverse direction, right? Whereas the other reactant for the reverse reaction would be HS minus. So in the reverse direction, HS minus is changing to H2S. So this right here has accepted the proton. An acceptor of proton is a base. So that makes this a base. So if the forward reaction is happening, this is an acid, ammonia is the base. In the reverse reaction, NH4 plus is the acid and HS minus is the base. So that essentially makes this acid and this base, which is its product, a conjugate acid-base pair. Same applies to the other reactant, which in this case, ammonia we know is the base, and the product that ammonia creates is NH4 plus, which is an acid. So that makes this an acid-base pair. So essentially, I would say the major difference between an acid-base pair, for instance, right here, is a proton. So H2S has one extra proton, HS minus has one less proton. So these two differ by just one proton. So the two substances that differ from each other by one proton are referred to as the conjugate acid-base pair. For instance, right here again, NH4 plus and ammonia. Ammonia has one less proton, NH4 plus has one more proton. So the difference in these two substances is essentially just one proton. And that is what makes this an acid-base pair. So essentially, just remember whatever's an acid on the left side of the arrow will produce its conjugate base on the right. Whatever's a base on the left side of the arrow is going to produce an acid, its conjugate acid pair. Okay. Here are a few more examples for you to practice. How can you figure out which one is an acid-base pair? So for instance, in this case, my advice is don't look at the answers right now. Try to do this by yourself. So for instance, we'll pick the first one. What's happening in the first reaction is HF is reacting with water to produce F minus and H3O plus. So let's try and form our conjugate acid-base pairs here. So let's first see, let's look at HF now. So HF right here is getting converted into F minus. So what happened here is that HF donated its proton. It lost the proton, right? So that makes HF an acid. And its product is going to be its conjugate base. So an acid will produce its conjugate base. What happened to water in this case? Water here changed into H3O plus. So what happened here is that it has accepted a proton, right? That makes water a base, and its product is going to be a conjugate acid. So what are the two acid-base pairs involved in this reaction? In this reaction, one of the acid-base pair is HF and F minus, and the second acid-base pair is acid. I would write the acid first since I'm calling it as an acid-base pair. H3O plus is the acid, and H2O is its base. Right? So these are just some conjugate acid-base pairs. And the difference, again, you can see here is just one proton between these two, and again in these two is again it's one proton. Right? So that's fairly simple to figure out what is the conjugate acid-base pair for a given acid or a given base. Once it says it's a base, you know base is going to accept a proton, and when it says this is an acid, for instance, if I ask here, let's pick this example, this is an acid, it's sulfuric acid, H2SO4, and I ask you what would be its conjugate base. The conjugate base difference is going to be just one proton. So it's going to lose one of the protons. So you essentially just take off one proton from here. What would be left is one H out of the two and SO4. And since this lost one proton, it lost one H plus, right? Since it lost a plus charge, it's going to be a negative charge right here. So it's going to be HSO4 minus, and this would be its conjugate base. Okay. Let's pick another example. So for instance, another acid could be HPO4 2 minus. And I'm telling you this is an acid, so can you tell me what would be the conjugate base for this? So we know that since this is an acid, it is going to lose one of the protons, right? So we have to remove one of the protons from here. If we remove this proton, what would be left? It's going to be PO4, and this was 2 minus, it lost one proton, so it has to have a new charge that is going to be 3 minus. So this would be its conjugate base. Okay? Now, if for the same example, I say that we have HPO4 2 minus, and I'm saying that this is a base. Can you tell me what would be its conjugate acid? Okay, so in this case, we know that if this is a base, the definition of base is something that accepts a proton. So this is going to accept one of the protons. If it accepts a proton, what would it change to? The formula would become, it has one extra proton now, so it's going to be H2 PO4, and now since it was 2 minus, it also took one more plus, so that makes 2 minus plus 1 as minus. So now this is its conjugate acid. So essentially, whenever there's an acid-base pair, if one is given, the other one would be based on what, if it's an acid or a base, you're going to either remove a proton or add a proton. Okay? So if you take a look at this example right here, NH4, we'll take one more quick example. NH4 plus is reacting with CO3 2 minus, and it's producing ammonia plus HCO3 minus. So we have to figure out which one's an acid, which one's a base first, in order to figure out what are the pairs. So let's first begin with the first reactant, which is NH4 plus. And what has it changed into? It was converted into ammonia. So NH4 plus changed into NH3. So the difference that you see here is one proton, and it was lost. So if it lost a proton, meaning it donated the proton, that makes this an acid, and its product is going to be its conjugate base. Now let's look at the other reactant. This is CO3 2 minus has changed into HCO3 minus, right? So what has changed here? It has accepted a proton. So if this accepted a proton, that makes this a proton acceptor is a base, and that makes this product right here automatically its conjugate acid. A base makes a conjugate acid, and acid makes a conjugate base. So our pairs are going to be NH4 plus and ammonia, and HCO3 minus and CO3 2 minus. So these are acid-base pairs for this particular reaction. So my advice here would be that you practice making the conjugate acid-base pairs for all of these reactions. And if you have questions, you can write in the comments of this video as well, or you can ask me by email. Now let me actually pull this back right here. So you see how in this particular example we had HPO4 2 minus right here that I said acted as an acid, right? And in this case, we had HPO4 2 minus, and I said this is a base, right? So the same compound, nothing has changed. It's HPO4 2 minus. This is an acid, whereas in this particular case, it's acting as a base. Such substances that can act both as an acid or a base are called as amphoteric substances. Given on the circumstances, given on what is the other reactant that it's reacting with, these compounds can act either as an acid or as a base. For instance, another example, oh, come on. For instance, like here in this example, we see this particular substance, HCO3 minus is reacting with OH minus to produce CO3, 2 minus, and water. Okay. So in this case, let's define if this is an acid or a base. So we know that HCO3 minus right here has changed into CO3 2 minus. That is its product. So what happened here is that it donated one of the protons, right? So this donated proton to OH minus, which changed OH minus to water, and this changed into CO3 2 minus. So this has donated the proton that makes this an acid. Now let's look at the other example. So what's happening in the other example, HCO3 minus is reacting with H3O plus to produce H2CO3 and water. So what's happening in this particular reaction is, let's start from here. HCO3 minus is changing, there are only two products, right? So H3O3 minus is producing H2CO3. So what's happening here is you can see that it has actually accepted a proton from this, and therefore, if this has accepted a proton, that makes this particular compound a base in this reaction, right? So what's happening here is that HCO3 minus is acting as an acid in presence of OH minus, whereas in presence of H3O plus, it's acting as a base. So this is showing you that HCO3 minus is actually an amphoteric substance. If you will, it depends on what is the other reactant, and it's going to behave either as an acid or a base. So in this case, if HCO3 was added with a stronger base, it would act as an acid. And in this case, since there was another acid present in this case, HCO3 minus acted as a base and accepted proton from this particular acid. Now, which one's stronger and weaker, we'll come to that later on. But essentially, the idea is that you should understand what an amphoteric is. Okay. So let's try this question. Which of the following can act as an amphoteric substance? In the top example, we have four different options: CH3COOH, HCl, NO2 minus, and HPO4 2 minus. So an amphoteric substance will accept a proton or it can donate a proton. So for instance, in this particular compound right here, CH3COOH, this definitely has a proton to donate, and we'll come to this later on. I believe you guys probably are not familiar right now what a COOH is. So these essentially, whenever you see a group COOH, these are called as carboxylic acid. So anything, there can be any other group attached to COOH, but if there is a COOH group together, that essentially makes it a carboxylic acid. So these are usually acids, these are organic acids. If you have taken a little bit or familiar with a little bit of organic chemistry, then you would know this. But otherwise, just remember that if there's a group of COOH that makes an acid, that makes that particular substance a carboxylic acid. So it definitely has an H to donate. So this makes it an acid for sure. But can it accept a proton? If it accepts a proton, that's going to change the charge right here. So this does not accept a proton. On the second example we have is HCl. Again, this has a proton to donate. So yes, this can act as an acid for sure. But if it accepts a proton, that's going to make it completely unstable. So this cannot act as a base. Next example is NO2. Next option is NO2 minus. This actually does not have a proton to donate. It can accept a proton that would balance this charge for sure, but it does not have a proton that it can donate. So this cannot act as an acid. No. Next, we see HPO4 2 minus, and we saw that example where this can actually donate this proton to change into PO4 2 minus, which would make this an acid, or it can actually even accept a proton to become H2PO4 minus. That would make this a base. So this right here is an example of an amphoteric substance. Okay, let's do next part. Which of the following can act as a amphoteric substance? Again, same idea. PO4 3- can only accept a proton. It cannot donate. A proton has no proton to donate. CO3 2- again has no protons to donate. HNO3 can donate a proton, definitely has one proton right here, but it cannot accept because it's going to make this unbalanced. There is no way it's going to accept a proton. HSO3- on the other hand has a proton that it can donate, and it also can accept a proton because this has a negative charge, so it will accept a proton and become neutral. So this, in this case, HSO3- is our amphoteric substance. So next we'll discuss the acid-base properties of water. So another thing that you might have observed in the previous examples is that sometimes water acts as an acid and sometimes it acts as a base. So water is also one of the amphoteric substances. So what happens in case of water right here from this example, you can see this equation shows H2O, which is liquid, changes to H+, which is aqueous, and OH-, which is also aqueous. So water can actually donate a proton and it can also donate an OH-. But usually whenever there's a pure sample of water, just pure water, nothing else mixed into it, it usually dissociates to produce H+ and OH- by itself. There's an equilibrium reaction to between the water, which is in liquid form, and the ions, which is H+, proton, or OH-. H+ is called the proton, OH- is referred to as the hydroxide ion. And this process or this reaction is known as autoionization or self-ionization of water. The water essentially just donates its own electrons. This oxygen has this extra pair of lone pair that it donates to this H and changes to H3O plus and OH-. This bottom reaction that you see right here, H2O plus H2O, one of these water molecules is going to donate a proton and the other is going to accept it, changing this to H3O plus and OH-. So whichever water molecule is donating the proton acts as an acid while the other acts as a base. So this is where water is essentially just reacting it with itself. And this particular reaction is at equilibrium. So we know from now, whenever reactions are at, we know now that whenever reactions are at equilibrium, or the reactions that can reach equilibrium, they always have an equilibrium constant associated with them. So in this case, the equilibrium constant for this reaction will be written out as Kc equals, it's always products over reactants. So product in this case is H plus times OH- over reactants. And in this case, you can see the reactant here is L, meaning it's a liquid. And if you guys remember from the previous video, liquids and solids are not included in the expression of Kc or equilibrium constant. So equilibrium constant for water is essentially H plus OH-, or like we saw in the previous reaction, this same reaction can also be written out as water plus water changes to H3O plus OH-. So the idea of using proton H plus or H3O plus, which is a hydronium ion, these two are used interchangeably. You're going to see in this topic, in this chapter, that these two are used interchangeably. They essentially just mean the same thing, that water has accepted a proton, or water here has donated a proton. So these both are just referring to proton per se. This is just proton by itself. This is proton with water. So in this case, this equilibrium constant of autoionization of water is also referred to as Kw. So instead of C here, since this is specific to water, it's referred to as Kw, meaning ion product of water. This is also called as ion product of water. And the value for this particular ionization, autoionization of water is 1.0 times 10 raised to power minus 14 at 25 degrees Celsius. We know now that values of equilibrium constant are specific to a certain temperature. As the temperature changes, these value changes. So whenever you see these values now, you will see a temperature associated with them. So at 25 degrees Celsius, autoionization of water has an equilibrium constant of 1.0 times 10 raised to power minus 14. And you should know this number. Remember this number. Okay, so let's see right here. So in case of pure water, Kw, which is H ion concentration times OH ion concentration, is going to be equal to 1 times 10 raised to power minus 14. So if you want to calculate what are the equilibrium concentration of H plus and OH minus, it is going to be essentially square root of this number, which is 1.0 times 10 raised to power minus 7. So this number right here is very important. This is what makes water neutral. This is how all the acids and bases have actually been defined. So whenever in case of water, the concentration of H ion, which is proton, and hydroxide ion is equal right here. Whenever H ion concentration and OH ion concentration is equal, that particular solution is regarded as neutral. For instance, in this case, pure water, there's nothing else added to it. It's always neutral. So the solution is regarded as neutral. Whenever the concentration of H plus is increased, that solution is regarded as acidic. And whenever the H ion concentration is lesser than the hydroxide ion concentration, that solution is regarded as a basic solution. Okay, so essentially this is showing you the same relationship again. Kw, whenever proton concentration, again H plus and H3O plus can be used interchangeably. Whenever this is equal to H minus, it's a neutral solution. Whenever the concentration of the proton increases in comparison to hydroxide, it's an acidic solution. Whenever the concentration of proton decreases in comparison to hydroxide, it's a basic solution. So let's try a couple questions now. So the concentration of hydroxide ion in a certain household ammonia cleaning solution is 0.0025 molar. Calculate the concentration of proton. So how do we solve this question? Let's first write down what's given to us. The concentration of OH minus is given to us. So we know that OH minus concentration is 0.0025 molar. And the question is asking what is the concentration of proton. We know that whenever we are just talking about a solution in water, always the concentration of proton times the concentration of OH minus is equal to Kw. And this Kw at 25 degrees Celsius is a fixed number. So if the temperature in the question is not given to you, assume it's talking about room temperature, which is 25 degrees Celsius. So in this case, Kw, we know the value of Kw is 1.0 times 10 raised to power minus 14. As I said, you have to remember this number. It will not be provided to you. Kw is 1.0 times 10 raised to power minus 14. OH minus concentration is given to us, which is 0.0025 molar times the H ion concentration. So everything's given to us except one value. We can easily figure that out. If we divide both the sides by 0.0025 molar, it's going to give us the concentration of proton, which would be 1.0 times 10 raised to power minus 14 divided by 0.0025 molar, which is essentially 4 times 10 raised to power minus 12, I believe. Okay, oh, what? Was this moving? Oh, no. Okay, so yeah, it's 4.0 times 10 raised to power minus 12 molar. Okay. So essentially, if we know one of these concentrations, we can easily figure out the concentration of the other. If we know proton or if we know the hydroxide ion concentration, one of them, we can easily figure out the other because Kw is always going to be a constant term. The next terminology that is very commonly used when it comes to acids and bases is how. So P here is essentially like a function that is used in chemistry. So for instance, if I have pH, that essentially means I'm talking about negative log of H ion concentration. So whatever is next to this P, you take negative log of that and you get that value. For instance, if I take pKw, I'm talking about negative log of Kw. If I say POH, I'm talking about negative log of OH ion concentration. P of whatever Px is negative log of X. So P right here is a very commonly used function. Then pH is the measure of acidity. So it tells us how acidic our solution is. So for instance, we know that at neutral conditions, H ion and OH ion concentration is this. So if you take negative log of that, pH comes out to be 7. So for a neutral solution, pH is 7. For an acidic solution, pH, H ion concentration is going to be higher than 10 to the power negative 7, which means that pH is always going to be lower than 7. And for a basic solution, since H ion concentration is going to be less than 1.0 times 10 raised to power minus 7, pH is always going to be greater than 7. So this gives us one scale to measure the acidity, and our scale essentially goes till 14. Oh, and there's this midpoint in between at 7, which is neutral. And if our pH, this is a scale of pH, if pH is less than 7, it's going to be acidic. And if it's greater than 7 right here, between 7 and 14, that means we are talking about a base. Our solution is basic in nature. So the lower the pH, the more acidic the solution is. The higher is the value of the pH, the less acidic the solution is, or more basic the solution is. So you can see right here, pH is negative log of H ion, so that negative sign essentially just makes it inversely proportional. So higher the concentration of the H ion, the lower is going to be the pH. Okay. So, like I said, POH is going to be negative log of OH. pH is very commonly used to um, explain the terminology of acids and bases, but POH is also a term that is also commonly used. You might not see as frequent as pH, but POH is negative log of OH ion concentration. And we already know that H ion concentration times the OH ion concentration equals Kw, which is 1 times 10 raised to the power negative 14. So if we take P or negative log of all of these, so negative log of this right here on the left side is going to give us negative log of H ion plus negative log of OH ion. So whenever it's in multiplication, when you take log of anything in multiplication, that becomes added up. And here, since this negative sign essentially is coming from the negative log, and Kw is 10 raised to power this. So if I take negative log of that, that would give me 14. So we can say that pH plus POH is going to be 14. So these are some formulas that you should always know. Like I said, here our scale is between of pH is between 0 and 14, or essentially 1 and 14. And this formula right here shows that pH plus POH is 14. So if we know one of these, we can figure out what would be the other one. Same thing applies here. If we know one of these between H ion and OH ion, we can figure out what is the other one. For instance, let's try this question. The concentration of H ion in a bottle of table wine was 3.2 times 10 raised to the power negative 4 molar. Right after the cork was removed, only half of the wine was consumed. The other half, after it had been standing open to the air for a month, was found to have a hydrogen ion concentration equal to 1.0 times 10 raised to the power minus 3. Calculate the pH of the wine on these two occasions. The first occasion, the question is asking for what is the pH of the wine. So we know that pH is negative log of H ion concentration. So if we have H ion concentration, we can figure out pH. Do we have H ion concentration? For both the instances, H ion concentration is provided to us. So in the first condition, in the first condition, pH would be negative log of the H ion concentration, which is right here, 3.2 times 10 raised to the power negative 4 molar. And the second situation, pH is going to be negative log of the H ion concentration then, which is 1.0 times 10 raised to the power negative 3. So you can simply plug in the values into the calculator and figure out what is the concentration. For this right here, it's easy enough. Negative log of anything, this is 1, 10 raised to the power minus 3 is going to be 3. And this you guys can figure out through calculator, and the answer is actually written out in the next slide. I think it comes out to 3.49 here, so the answers are also provided to you. Okay, let's try the next question. So the pH of rainwater collected in a certain region of the northeastern United States on a particular day was 4.82. Calculate the H ion concentration of rainwater. So now what's given to us, the information that's provided to us in this question is the pH of the solution. So pH is 4.82. The question is asking calculate the H ion concentration. What is the concentration? We know that pH is negative log of H ion. So 4.82 is negative log of H ion concentration. Now we have to solve for this. How do you solve for this? Whenever you have log, and this is to the base 10, if we raise both the sides to the power of 10, that would cancel log. So 10 raised to power, and since this is negative, you have to cancel that negative sign as well. So this would become 10 raised to power negative 4.82 would be equal to concentration of H ion. And if you plug this into the calculator, that should give us the concentration of H ion, which comes out to 1.5 times 10 raised to the power minus 5 molar. So pH is negative this, and to cancel negative, we multiply both the sides by negative. That makes log H ion minus 4.82, and then you just raise everything to the power of 10. Okay. Next question is in a sodium hydroxide solution. OH ion concentration is 2.9 times 10 raised to the power minus 4 molar. Calculate pH of the solution. So now what's given to us, we have a basic solution. The concentration given to us is OH minus equals 2.9 times 10 raised to the power minus 4 molar. The question is asking what is the pH of the solution. So first thing we have to notice here, what's given to us is not the H ion concentration. What's given to us is OH ion concentration. Now there are two ways we can solve this question. Let's check the first way first. So if you have the OH ion concentration, I cannot calculate pH, but I can calculate POH. POH is going to be negative log of OH ion, meaning negative log of this right here, which is 2.9 times 10 raised to the power minus 4. That if you plug into your calculator would give you a value of 3.54. So now that I know the pOH of my solution, right here. So this is the this is the pOH value of my solution. Right, what I want to solve is pH. Do we know a relationship that relates pH and pOH? Yes, we know that pH plus pOH is 14. So pH is going to be 14 minus pOH, which is minus 3.54. That would give you a value of 10 point something. So, oh, right here, 10.46. So this would be our pH of the solution. Now there's another way, like I said, you could use another approach to solve for this question. So let's see what that other approach could be. I'm gonna mark this. Okay, I'm gonna mark this and try to solve for the other part, the other alternative way. So I know that OH ion concentration is 2.9 times 10 raised to the power minus 4. Now, we also know that H ion concentration times OH ion concentration equals Kw. So if we want to figure out what is our H ion concentration, that would be Kw divided by OH ion concentration. We already know what's the value for Kw, we already know what's the value of OH ion, so we can plug in those numbers. This would be 1.0 times 10 raised to the power minus 14 divided by the value that's given to us, 2.9 times 10 raised to the power minus 4, and we can solve for what is the H ion concentration. Once we know what is the H ion concentration, we can solve for pH. So this will come out to 3.4 times 10 raised to the power negative 11. Now since we have the concentration of H ion, this is our proton concentration. Since we have solved for this, we can calculate pH, which would be negative log of H ion. So it's equal negative log of the value that we just calculated. And if you plug in this number into your calculator, that would give you 10.46. So same answer like the other approach. So these are two approaches you can use. You should know both these equations, that H ion times OH ion concentration is Kw, and you should also know that pH plus pOH is 14. Either way, you should be able to calculate the pH of the solution. All right, let's try another example. This example says determine the OH ion and H ion concentration given the pH. What are the proton and hydroxide ion concentration for a solution where the pH is 3? So again, there are two different ways we can solve this question. I feel the easier way is if I calculate the pH and pOH. So the pH is given to me as 3.00. The question is asking me to solve for proton concentration and hydroxide ion concentration. So if I know the pH, it's easy. I can calculate what is the proton concentration. pH is 3. pH is negative log of H ion. So 3 is negative log of H ion. And if I want to solve for this, I raise both the sides to the power of 10. First thing I have to get rid of this negative sign, meaning negative 3 equals log of proton concentration. Now I raise both to the power of 10 equals proton concentration, meaning this is essentially 1.0 times 10 raised to the power negative 3. So this is 1.0 times 10 raised to the power negative 3. Now that I know my proton, it's equal 1.0 times 10 raised to the power negative 3 molar. So now that I know the concentration of H ion, I can figure out the concentration of OH ion. Why? Because we know that proton times hydroxide ion concentration equals Kw. So hydroxide ion is going to be Kw over proton, and Kw is 1.0 times 10 raised to the power minus 14 divided by 1.0 times 10 raised to the power minus, and that is 1.0 times 10 raised to the power 1.0 times 10 raised to the power minus 11 molar. So this is our H ion concentration and this is OH ion concentration. Here we go. I'll leave the next question for you guys to try and I'll move on to the next concept which is, we have been saying in the beginning of this lecture that some acids are strong while some acids are weak. So what do we mean by that? Here are some examples of the strong acid and strong bases. There are 6 strong acids, including perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. And here are the 6 strong bases. I would want you guys to memorize these. So you should know, once you look at an acid, an example of an acid or an example of a base, you should be able to identify if it is a strong acid or base or if it's a weak one. So anything that you see other than these is a weak acid or a weak base. Okay, so you should definitely memorize these: lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. These are examples of the strong bases. Okay, now how do we know, or what decides if something is regarded as a strong acid or a weak acid? That depends on its equilibrium constant, how it behaves when it is dissociating in presence of water. So what that essentially means, we know that for an acid, essentially is HA. Let's take an example, an acid. We'll assume it's HA because acid usually have a proton. So HA right here is going to interact with water, which is liquid, and it will dissociate to produce H3O plus and A minus. So that's usually how our reaction is, and we know these reactions are mostly in equilibrium. Now this is where everything lies. So if it's a strong acid completely dissociates, meaning that instead of being in an equilibrium, oops, the reaction goes completely towards the product. So all the acid in presence of water dissociates to produce protons and its conjugate base. This such acid is called as a strong acid. When we have this kind of an acid, you will actually, in presence of water, you're not going to see any HA present. The equilibrium essentially is all shifted towards its product. Therefore, since there is no equilibrium, these acids do not actually have their K equilibrium constant is almost unimaginable. It's like regarded as an infinite number. So the equilibrium constant does not apply to a strong acid or a strong base. A weak acid, on the other hand, in case of a weak acid, the equilibrium is actually established, because of which not all acid is converted into the protons. So not all acid dissociates, only some of this acid dissociates to form ions in water, and that's why such acids are called as weak acids. So in this case, what would be the expression for Kc? The Kc would be product, so H3O plus times the second product, which is A minus, divided by the reactants. In this case, it's going to be our acid HA, and water, since it's a liquid, we are going to leave and ignore that water. So this would be expression for our equilibrium constant. And since we know that in this particular reaction we are talking about dissociation of an acid, so we usually refer to this term Kc as Ka, which is also called as the dissociation constant for an acid. Dissociation constant for an acid, or acid dissociation constant, Ka, because A for the acid. Right? So it's specific towards acid. Each acid has its own Ka value at a given temperature. And we know from equilibrium, a larger value of Ka essentially means that the reaction is going more towards the product. So an acid which is stronger, again, we are talking about weak acids in this case. Strong acids don't have an equilibrium constant. Now the stronger acids out of all the weak acids is going to have a higher value of Ka. So the larger is going to be the Ka, stronger would be that particular acid, since it would have more protons being dissociated. So as you can see right here, value of Ka is an indication for the strength of an acid. For strong acid, the concentration of HA is 0 and the acid dissociation constant is immeasurably large. Therefore, Ka is like, we don't talk about Ka for a strong acid. For weak acid, larger the Ka, stronger the acid. Now this is about Ka. So right here, larger the Ka, stronger is the acid, which means if I take pKa, it's going to be reverse relationship. So the larger the pKa, weaker would be the acid. Why? Because pKa essentially is negative log of Ka. So we basically make this relationship inverse. Larger the pKa, weaker would be the acid. Smaller the pKa, stronger would be the acid. Okay. For instance, here are some of the values for Ka values for some of the weak acids. For instance, we have formic acid, acetic acid right here, hypochlorous acid. So all of these acids, you actually do not see the strong acids that were shown to you in the previous slide. So if you don't see a strong acid that you have memorized, that means that it's a weak acid. So all of these weak acids, you can see here are the Ka values, and you can see the acid strength is increasing from bottom to top. Why? Because we can see that the Ka values are increasing from bottom to top. Higher the Ka value, higher is the strength of the acid. The same concept applies in case of bases. So a very strong base will not have a dissociation constant associated with it. A strong base is going to completely dissociate or completely ionize into ions when added into water. But for a weak base, when it dissolves in water, there is an equilibrium established such that only some of it will be dissociated. And the dissociation constant or the equilibrium constant for a base is represented by Kb. It's also called as base dissociation constant or base ionization constant. B stands for the base, and it's given by BH plus OH minus divided by B. Okay, same concept as acid. And here are some of the examples of the bases, Kb values. These are some of the weak bases. Right here, for instance, ammonia, aniline, methylamine, all these are weak bases, and you can see the Kb values are provided as well. And as the Kb value is increasing, as we go from bottom to top, the strength of the base is also increasing. Now, another thing that you would notice, let's write down the dissociation constant. Now, another important concept that, or the important formula that I would like you guys to memorize is that Ka times Kb equals Kw. Okay, this is just it rearranged, but essentially the important idea is that Ka times Kb equals Kw. Ka is the dissociation constant of an acid, Kb is the dissociation constant of the base, and Kw is the ionization constant of the water. Okay. How can we derive this equation? So let's quickly look at that. So if I'm talking about an acid, Ha plus water, would Ha is an acid, so it's going to donate its proton to water to form H3O plus A minus. So in this case, this is our acid, and now we know that A minus is the product from Ha, so this is our base. So when we are talking about a conjugate acid base pair, so in this case, A minus is our base. Now if we have A minus in presence of water, how is it going to react? Since this is a base, it is going to accept protons from water. It will accept the proton and it will change into Ha, and proton will change into OH minus. Since this is equilibrium for an acid, we can write it as Ka. Ka will be product, so H3O plus times A minus divided by Ha. And since this is a base, the reaction is essentially for a base. We'll write this as Kb, which would be equal to products Ha times OH concentration over A minus. Water here is liquid, so it has been ignored in both cases. Now, we have already seen if we want to combine the two reactions, we can combine it. Ha gets cancelled, A minus gets cancelled, and this is our overall equation. So in this case, if you're talking about overall equation, what happens to K's? The K gets multiplied. So the overall equation Kc is going to be Ka times Kb as written out right here. So if I plug in these values, it gives me, if I multiply Ka times Kb, Ha gets cancelled, A minus gets cancelled, I'm left with H ion times OH ion. And what is this? This is essentially same as Kw. So I can write this Ka times Kb equals Kw. That's how you essentially get this equation. What this relationship is telling you is that Ka and Kb are inversely proportional for a conjugate acid-base pair. So if an acid is a strong acid, its conjugate base is always going to be a weaker conjugate base. Okay, if Ha is a very strong acid, its base is going to be a weaker base. So in comparison, both of these would always be inversely proportional to each other. Now I would like to try out some examples for this concept, but before we run into the examples, I want to go over another concept, which is really simple concept. It's essentially called percent ionization. So percent is same idea, percent. In this case, we are talking about percent ionization. When we say percent ionization of an acid, so our acid is Ha, it's going to dissociate to produce H plus A minus. H plus, we can also write it as H3O plus, same thing. So if this is the dissociation of our acid, we know it's in equilibrium, not all of the acid is dissociating. So this is our dissociated acid, the amount of acid that has dissociated. This is the amount of acid that we began with right? So same concept, how do you figure out percentages? If we say percent yield of a reaction, in this case, since we're talking about ionization of an acid, we, instead of writing it as the percent yield of the reaction, we refer to it as percent ionization. So percent ionization would be how much of it the acid has already ionized, so HA concentration that is already dissociated, or the starting concentration of HA initial that we began with times 100. That's the percent ionization for an acid. So how much is the amount that has dissociated? If I know what is the concentration of A minus, then that would be my amount of acid that has dissociated. If I know is the initial concentration of HA, that's my initial, times 100. So this would give me the percent ionization of a given acid. So we know for a weak acid, this percent ionization is going to be smaller. For a strong acid, since all of it gets dissociated, the percent ionization is going to be 100%. And that's why for a strong acid, it's always 100%. For a weak acid, it's low. And as more and more of the acid dissociates, the percent ionization slowly decreases. Okay, perfect. So if we know these concepts, now let's try some questions. Okay. Oh, and here are some of the normal, very generic rules of log that you should be familiar with. They'll come handy. So if I have something like log A times B, which I said before in the lecture as well, it's going to be equal to log A plus log B. So if you open the parentheses in case of log, it actually becomes plus. If we have log A to the power of B, and these are all base 10, these logs. So log A to the power of B, and if I want, this is going to be equal to B times log A. If we have log A over B, that becomes log A minus log B. Right? So some basic rules of log. Okay, so let's try this question then. So the question says calculate the H ion concentration, pH, H ion concentration, and pOH for each solution at 25 degrees Celsius. So let's try part A. A is 0.30 molar HNO3 used for etching copper metal. Okay, so what's given to us in the question? Let's try part A. The question says we have 0.30 molar HNO3. The question is figure out the H ion concentration, OH ion concentration, comma, pH, and pOH. All these we have to solve for a solution of nitric acid. Now, the first thing that we always ask whenever the question is something like this is it a strong acid or is it a weak acid? So we know nitric acid, HNO3, is an acid. Now, is it a strong one? So you will go back to the table that you saw. You should have actually memorized it. So based on that table, you realize HNO3 is a very strong acid. So if you're talking about a strong acid, I'm going to take the example of HA. It completely dissociates. There's no equilibrium here to produce the A minus and proton. So if whatever is the concentration of your strong acid, if this was 0.30, at the end we will have 0.30 molar of proton produced. Why? Because it's a strong acid, all of it is going to dissociate. So now, what would be the concentration of my proton? It's going to be 0.30 molar. If this is the concentration of protons, what would be the pH? pH is going to be negative log of 0.30 molar. If you plug in this value in the calculator, it will give you 0.52 as your pH. Again, pH does not have a unit. This is a dimensionless quantity. So now that I have the pH, the next part I need is the OH ion concentration. We know that H ion times OH ion equals Kw. So I can simply plug in my H ion concentration here, and my OH ion will be Kw over, H ion concentration. Okay, let me rewrite that. Okay, so we already know this, we just have to solve for OH ion concentration will be Kw divided by proton. Kw is 1.0 times 10 raised to the power minus 14 divided by H ion is 0.30, and this will give you answer of 3.33 times 10 raised to the power minus 14 molar. So this is now my OH ion concentration. If I have OH ion, I can solve for pOH, which will be negative log of OH ion concentration. So negative log of 3.3 times 10 raised to the power minus 14. And if you solve for this, this will give you something 13.4 or 38 or something. So let's confirm. Okay, 13.48. All right. So that's how you solve for the H ion and OH ion concentration. This is for a strong acid. Okay, for a strong acid, whatever is the concentration of the acid, you can assume that would be the H ion concentration. This is a monoprotic acid. Now, what is a monoprotic acid? An acid that only has one proton to donate. For instance, right here, this acid only has one proton. Okay, so this is called a monoprotic acid. There are also polyprotic acid. Okay, for instance, H3PO4 is a polyprotic acid. It has 3 protons that it can donate. Another example is H2SO4. This has 2 protons that it can donate. Okay, so depending on how many protons an acid has, it can be referred to as monoprotic, diprotic, polyprotic. All right. Okay, let's try the next question, which is, okay, so what I have now is 0.0042 molar calcium hydroxide. The question is still the same. I need H ion, OH ion concentrations, and pH and pOH. So in this case, this is a base, right? How do I know that? I know it from the OH ion that I see right here. This is the first definition of the acid and base that was given. So if there is an OH ion, that means that this is more like a base. And if you have memorized your table, you will know this is a strong base. So since this is a strong base, it's the same concept. All the base is going to be donating all its OH ion or accepting all the protons. So all the base is going to dissociate. So all calcium hydroxide in this case is going to dissociate to produce calcium ion plus hydroxide ion. And in this case, each calcium hydroxide has 2 hydroxide ions. So my concentration of hydroxide ion is going to be twice. So if my calcium hydroxide is 0.0042 molar, the amount of hydroxide produced would be twice of that. So it will be 0.0084 molar. So that's why it's important to know if how many protons or how many hydroxides are involved with acids or bases. So now I have solved for the first part, which is my hydroxide ion concentration is 0.0084 molar. Next is I can easily solve for pOH right here, which will be negative log of this. I'll let you guys figure out the answer. Plug this into your calculator and get your final answer. The next thing I can solve from here, one is easy approach. You can use that, which is pH. I'll use a different approach this time. So you can use whichever one you feel comfortable with. In this case, since I know the pOH, pH plus pOH is 14. So my pH will be 14 minus pOH, which is whatever you get here. You can subtract it and get your answer. Okay. Another idea like we used in the previous question. I know that OH ion concentration times the H ion concentration equals Kw. So if I already know this OH ion, I can figure out what is the H ion concentration. H ion concentration will be Kw over OH ion concentration. So 1.0 times 10 raised to the power minus 14 over OH ion, which is 0.0084. So you can solve for H ion concentration based off of this and get your answer, and then figure out the pH. Either way, whichever way works is easier for you, you can use that. Both would give you the same answer. Okay, so all the numbers are right here. Strong electrolyte, this is the OH ion concentration. If I calculated the pOH, then calculated the H ion concentration and got the pH from there, taking negative log of H ion concentration. Okay, let's try the next question. Now this was when we were talking about a strong acid or a strong base. So if you have a strong acid, whatever is the concentration of the acid is the concentration of the proton. Easy enough, right? What happens if it's a weak acid? In case of a weak acid, the reaction is not as straightforward as this. The ionization is not 100%. In case of a weak acid, we know that it's now a case of equilibrium. So Ha will dissociate, but in equilibrium to produce H ion plus A minus, right? This is aqueous, and this is aqueous, right? So now how can we figure out what is the H ion concentration? If you guys remember from equilibrium, if the reaction is at equilibrium and we have to figure out any of these concentrations, what do we use? We use ice table. So the same concept is going to carry over now. I know the concentration of my acid to begin with, let's say it was 0.3 molar. This was going to be 0, 0 changes minus x plus x plus x. This is going to be 0.3 minus x, x, and x. So I'm going to plug this in, figure out what is the Ka for this reaction, and use my concept of equilibrium constant to figure out what is the concentration of H ion right here. Okay, Oh, there we have an example. I did not intend to open that up, but it's right here. So let's try and solve one question. Okay, the question is to calculate pH of a 0 point. So what's given to us is 0.036 molar nitrous acid, HNO2. Calculate the pH of this solution. Reaction is given to us and Ka is given to us. Ka is 4.5 times 10 raised to power minus 4. So if a Ka value is given to you, first thing that should come to your mind is that this is a weak acid, because strong acids don't have a Ka value. So the first thing is that this is a weak acid. Second thing is you can also see it from the formula. You have already memorized the table and you know based on that table, this is a weak acid. Okay. So we're going to write down this equation. Either you can write this or you can just go with the generic equation, which is Ha, for instance, HNO2 will dissociate to produce H plus, aqueous, A minus, aqueous. Remember, everything is aqueous in this case. If you add water, if you choose to write down water right here, Ha plus water, that's okay too. Ha plus water gives H3O plus and A minus. Just remember that that water here is going to be liquid. Okay. So in this case, if I'm writing this equation for dissociation of my HNO2, I want to figure out the pH. For pH, I need the H ion concentration at equilibrium. To solve for H ion concentration at equilibrium, I need to make ice table. So I will create my ice table right here. What am I beginning with? I have 0.036. Now this is no longer an acid-base question. This is more like the equilibrium constant question. So if you understand those concepts, you just have to plug in the same numbers. This is molarity. Remember, everything that goes in this table is molarity. So 0.036. Initially, we don't have any products, so 0 minus x, stoichiometric coefficient is 1, plus x, plus x. I'm left with 0.036 minus x, and x. Right? So based off of this, I can write down that my expression, how do I solve for x? Remember Kc, in this case it's going to be Ka since this is an acid. It will be proton concentration times minus A minus concentration over Ha concentration, since all of them are in aqueous form. So I'm going to plug in all these numbers into this expression where Ka is given to us in question. It's 4.5 times 10 raised to power minus 4 equals, this is x right here from the ice table. So it becomes x squared divided by 0.036 minus x. Now this is what we have done in equilibrium. So we just solve for x. How do we solve for x? Remember, this is a quadratic equation now, so we are going to make our assumption. So I'm going to go back to my presentation since it's easier. Ice table right here. We are going to make the assumption that 0.036 minus x is same as 0.036, and that would give us, reduce our expression to this, solve for x, it will give you a value of 4.0 times 10 raised to power minus 3. Now, once we have a value of x, the first thing that you have to do is verify that or check for your approximation if the approximation that we have made is correct or not. And how do we verify that? That would be x over the initial concentration times 100, that is 11%. Unfortunately, this value is greater than 5, so our approximation is not valid. We'll have to actually solve the quadratic equation, which is x equals minus b plus minus square root of b square minus 4ac over 2a. But remember, in exam, I'm not going to give you a question like this where the x assumption will not come out to be true, since this isn't a math class or how to use a calculator class. But you should make sure that you actually solve for the approximation. Okay, you have to show me that you do understand these steps, though. That in this question like this, you will be confirming that your assumption is correct or not. Right? Once you have your value of x, that's our H ion concentration, and pH is going to be negative log of that. So here we have our pH of 2.42. That is the answer for this question. So whenever you have a strong acid, whatever is the concentration of the acid, that is the concentration of the proton, as long as it only produces one proton in the reaction. And if it's a weak acid, we do the ice table. Let's try another question. The pH of a 0.1 molar solution of formic acid is 2.39. What is Ka for this acid? So now, in this question, what's given to us is that pH is 0.10 molar for formic acid. Again, formic acid, it doesn't fall under the table that we have learned from on the 6 strong acid. So this is supposed to be a weak acid. If you don't understand this, that's okay. You can see it's a COOH that I told you. If there's one COOH, it's going to donate one proton. So instead of writing this whole expression, I'm just going to go with my generic equation, which is HA dissociates in the equilibrium to produce HA plus A minus. The pH is 0. No, sorry, that's not the pH. The pH is 2.39, and the concentration of my acid is 0.10. So this is the concentration of acid that I began with. Now the question is, what is Ka for the acid? Again, this has come down to concept of equilibrium, right? If I know my initial concentration of acid and I want to figure out what is the Ka, for Ka I need the ice table, right? What is Ka? Ka would be the product over reactants. To figure out all those concentration, I need ice table. So let's create our ice table. Ice. What's our beginning concentration? 0.10. Initially 0 product. Change is going to be based on stoichiometric coefficient, which is minus x plus x plus x. That means it's 0.1 minus x, x, and x, right? So what is my expression for Ka? Ka would be HA concentration times the A minus concentration over HA, which will be x squared divided by 0.1 minus x. So I have to solve this, but I don't know what is the value of x. Is there any information that can help me solve the value of x? So let's see what is the information in this question that we have not used yet. We have not used the pH yet. So what is the information that I can get from pH? pH is 2.39. If I know the pH, I can find pOH. Another thing that I can find here is HI concentration. Will that help me? Yes. Whatever is the HI concentration at equilibrium, that is my value of x. So if I solve for HI, I have my value of x, and if I know the x, I can solve for Ka. So let's use that information. So pH equals negative log of HI. In this case, 2.39 is negative log of proton concentration. I want to get rid of the negative sign, so I'm multiplying both the sides by negative. That would give me negative 2.39 equals log of proton, and raising both the sides to the power of 10 would give me proton as 10 raised to power minus 2.39, which will be equal to, this comes out to 4.1 times 10 raised to power minus 3 molar. So now that I have my atom concentration, I can use this value to solve for, this is the value of x. This right here is x. So if I have x now, I can use this to calculate the value of Ka. So just plug in all the values of x into this expression and we can solve for Ka. So as shown in the answer right here, we got the value of x and we plugged in the value of x into the expression, and that would give us our Ka as 1.8 times 10 raised to power minus 4. Let's try the next question. Okay, so now let's try the next question. So the question says, in 2011, researchers showed that hypochlorous acid generated by white blood cells kills bacteria. Calculate the percent dissociation of A is 0.4 molar hypochlorous acid and B is 0.03 molar hypochlorous acid, and Ka for the acid is given to us. First thing, should write down what's given to us. So we're talking about hypochlorous acid, and based off of this acid, we know this is not part of the 6 strong acids that we have memorized, so we know for sure this is a weak acid. Another evidence that this is a weak acid is provided in the question, where it gives you the Ka value. So if Ka is given, that essentially means this is a weak acid. So let's focus on part A. Part A says that we have 0.40 molar hypochlorous acid, and Ka is given to us as 2.9 times 10 raised to power minus 8. So you can see the value of Ka is really small, right? So now the question is asking, calculate the percent dissociation. So what do we know for percent dissociation? Percent dissociation is essentially the acid. We can write it as a generic form, acid that is already dissociated divided by the initial amount of the acid that we began with times 100. So if we can figure out these two values, we would be able to figure out what is the percent dissociation for the acid. This is already given to us for the acid. The initial concentration of acid, we already have that. What we have to figure out is how much is the concentration once it has dissociated, right? And how do you figure that out? Again, remember, this is the dissociation of an acid. For let's write down the equation for that. It is going to be HClO. Since we're talking about a solution, it's going to be aqueous in presence of water. You can write include water here or not include water here. Wouldn't make much of a difference, but I would say make a habit of including water. Now, since this is an acid, what does an acid do? An acid donates a proton. So we know from here, this proton right here, H right here, is going to be donated to water, right? So in this case, water will act as base. Once this donates the proton, what will happen to the formula? It's going to be ClO. And since one of the protons is lost, H plus is lost, the charge is going to be negative. One negative. This is aqueous. And then the last product is going to be water, which would accept this proton and it would change into H3O plus aqueous. So if you would not include um, the water, in this case, the reaction will essentially be HClO changes to ClO minus plus H plus. That would do as well. But including the water is helpful and it's a good habit. So now if we know this equation, what do we have to figure out? We have to figure out what is the HClO that has dissociated and how much of it has dissociated. Whatever is the product that is produced, ClO minus, that is the HClO that has dissociated. Or we can also figure that out from how much of this has dissociated. But basically, what is the idea? How do you figure out the equilibrium concentration? Always, when we need to know the equilibrium, there's only one answer. It's ice table. So we'll begin with our ice table. What do we need for ice? The initial concentration. So what is our initial? 0. Oh, let me rewrite that. It's going to be 0.40 molar to begin with. Water is liquid, so we don't care about it. ClO initially is a product, so 0 and 0. Change is going to be minus x plus x plus x. Equilibrium would be 0.40 minus x, x, and x, right? So now that we have all these concentrations, we are looking for the amount that has dissociated. What is the amount that has dissociated? This right here, the change. How much of the ClO4 was actually used up in the reaction? X molar. So if we can solve for x, we have the dissociated amount and we can solve for percent dissociation. So let's try and solve for x. How can we solve for x? Equilibrium, ice table. So we know the only expression we can solve for is Ka. Ka in this case is going to be product, which is ClO minus times H3O plus over our acid HClO, and water is not included because it's a liquid. So if you plug in our numbers, Ka is given to us in the question. Ka is 2.9 times 10 raised to power minus 8 equals, oh, 10 raised to power minus 8 equals this right here. So we'll plug in the values. ClO minus is x, H3O plus is x. So it is going to be x squared divided by HClO, which is 0.40 minus x. Right now, I hope everybody knows how to solve for x in this case. We are going to make an assumption. Oh, let me just move this up right here. Okay, so now assuming that 0.40 minus x is same as 0.40, it would reduce down our equation to 2.9 times 10 raised to the power minus 8 equals x squared divided by 0.40. And from here, if we solve for x, not sure what do we get. So let's look for the number. X squared comes out to be 1.1 times 10 raised to the power minus 4 molar. So this is our x. Now remember, we have made an assumption. So the next step I do right here is to confirm or verify my assumption. So to verify assumption, it's going to be x over initial concentration of HA. So what is X? X is 1.1 times 10 raised to power minus 4 divided by initial, which is 2.9 times 10 raised to power minus 8. So this value comes out to be, if you plug into your calculator, it is 0.028%, which is definitely less. This is definitely less than 5%. So that essentially means this assumption is correct. And I can make this assumption, and my X value is this now. So once I have my X, we know based on our ICE table that X is the amount of acid that has dissociated. So now let's plug in the numbers in dissociated over initial. So our percent dissociation is going to be dissociated amount, which is 1.1 times 10 raised to power minus 4 divided by initial amount, which was 0.40 times 100. And that would give you how much of acid has actually dissociated. And oh, never mind. Oh, there. Oh, that was the answer of percent dissociation, not confirming the assumption. Okay, anyways, you should try and confirm the assumption. Let me write this down right here. So 1.1 times 10 raised to the minus 4, this is coming out to 0.028%. The So to confirm, x is going to be 1.1 times 10 raised to the power minus 4 divided by initial, which was 0.40, and you can see this is 10 raised to the power negative 4. So if you plug in this value, it's going to be definitely less than 5% or 0.05, which means my assumption is correct. So but you can try and plug this value into your calculator and see what is the exact value that you get. But the whole idea is we want to confirm this is less than 5%. It is. So my assumption is correct, meaning I can assume that x is 1.1 times 10 raised to the power minus 4. So now that I have the value of x, the question was to figure out what is the percent dissociation. And we can see from our ICE table that the amount of acid that has actually dissociated is x, and the initial amount we already have. So percent dissociation based off of this formula, which is dissociated over initial times 100, we can just plug in our numbers. So this would be equal to amount dissociated, which is 1 times 10 raised to the power minus 4. Initial was 0.40 times 100. And when you plug into the calculator, this would come out to 0.028%, meaning this is the amount of acid that has dissociated. All right. For part B, it's essentially just a different concentration. So I'll let you guys try that example yourself, and we'll move on to the next question, which is dimethylamine, a key intermediate in detergent manufacture, has a Kb of 5.9 times 10 raised to the power minus 4. What is the pH of 1.5 molar CH3 whole twice or dimethylamine? Okay, so what we have here is a base. How do I know we're talking about a base? Because the equilibrium constant that's given to me is Kb. So we know that this particular compound is a base and it's a weak base. So first thing is that should come to our mind. Now let's write down what's given to us. It's CH3 whole twice and H. Kb is given to us. Kb is 5.9 times 10 raised to the power minus 4. Question is asking that we have a 1.5 molar solution of this. What is the pH of the solution? So whenever you see a question like this, first thing you should do is that this is a base. So we'll first write out what is the equation for the base. Essentially, how will this base react with water? Okay, so let's try and write that equation. So this is CH3 whole twice NH aqueous. Since we're talking about a solution in water, it's going to react with water, which is liquid. And the question is telling us this is a base. What does a base do? A base accepts a proton. So in this case, water is going to donate a proton, and dimethylamine is going to accept a proton. So if it accepts a proton, what will happen to the formula? It's going to be CH3 whole twice NH2. And since an added proton H plus is added, the charge is going to increase and it's going to become plus. And this is aqueous. And there's going to be another. We make my board a little bit longer. Okay. Plus it will be, what happens to water here? Water donated the proton, so what's left now is OH minus, just the hydroxide. Okay, All right, so what's left here is just the hydroxide ion. So that's why you can see why writing out water in the expression or the equation is important, because in this case, for the base, we know that bases accept a proton, which it did here, and what's produced is an OH minus at the end, and this OH minus makes the solution basic. So it's easier when you have water provided, and then just go, if an acid is given to you or a base is given to you, an acid donates a proton, a base accepts a proton, and just think about the proton is going to come from water. Either it's donating it or it's accepting it, right? All right, so now the question is, I have 1.5 molar of this particular compound. The Kb is provided. What is the pH? What do I need for pH? I know that pH is negative log of H ion concentration. So if I know the H ion concentration, I can figure out pH. Do I see H ion here? I don't, but I do see an OH ion here. So we saw that if I can figure out what is the OH ion concentration, I can calculate the H ion concentration, right? And there's another approach we have seen in a couple questions before. There are two different approaches that you can use to go from pH to pOH. So first thing that I have to solve here is to get the what is the hydroxide ion concentration. So let's try and solve that. Whenever it's an equilibrium reaction, the easiest thing is that we know already that we'll have to use the ice table. So this is 1.5 molar. The water is liquid, so we don't care. This is 0 to begin with, 0 to begin with. Assuming we used up minus x, we'll produce x here, x of hydroxide. What's left at the end is 1.5 minus x, x, and x. Right? Now that I have my ice table, I can solve for x. If I know x, I would know what is my OH ion concentration. So how can we solve for x? We know that this is a base, so Kb is going to be equal the products, which is CH3 whole twice NH2 plus concentration times OH minus concentration divided by product, which is CH3 NH concentration, and we can ignore water since it's a liquid, right? So let's just plug in our values into this expression and try and solve for x. So Kb is provided to us in question. Kb is 5.9 times 10 raised to power minus 4 equals, we know this is x, making it x squared divided by 1.5 minus x. I'm getting these values from my ice table. So now again, if this is a quadratic equation, I'm going to make my assumption, assuming that 1.5 minus x is same as 1.5. Why am I making this assumption? Because we can see that the Kb is pretty small number, so the reaction is not going to make progress too much towards the product. So I can make this assumption. If I make this assumption, now my equation is essentially reduced to 5.9 times 10 raised to power minus 4 equals x squared divided by 1.5. And now I can simply solve for x. Let's see what value do we get for x from here. X comes out to be 3.0 times 10 raised to power minus 2 molar. So now that I have x, I will first have to confirm my assumption. So let's write down confirm assumption. How do you confirm? It's x over initial concentration. Oh, sorry, this is a base. So I'm going to write initial concentration. X is 3.0 times 10 raised to power minus 2 divided by 1.5, and that value when you plug in will come out to around 2.0%, which means this is less than 5%. So the assumption is justified. Since the assumption is justified, my x value, now I know this x is equal to OH ion concentration, right? From my table, I know this is the concentration of OH ion. If I know OH ion, now there are two ways that I can go. I'll do one of the ways. I'll solve one of the ways right here. If I know the OH ion, I can figure out what is POH, right? Remember, this is OH ion, so if I take negative log of that, that will not be my pH, that is going to be POH. So negative log of OH ion concentration, which is negative log of 3.0 times 10 raised to power minus 2, which if you plug in, I'm not sure what it comes out to. There we go. It comes out to 1.52. So that is the POH of the solution. Do not leave your question right here. That is not your final answer. That is POH. The question is asking pH. We know that pH plus POH equals 14. So I'm solving for pH. I know the POH. pH is going to be 14 minus POH, which is 1.52. So that comes out to 12.48. This is your final answer, right? Another way that I said we can solve for this question is I already know what is my OH ion concentration. We also know another formula, that is H ion concentration times UH ion concentration equals Kw. So we can use this to solve for the H ion concentration and then calculate pH from there. Both of them should give you the same answer. Each of them, any of these options is acceptable. All right. Okay, so that was the end of this topic. This is part one for acids and bases. And I would say please practice this again, go through this again, and I'll prepare the next video, and I'll see you guys in the next video then.